Today we shall discuss about derivative feedback controller. In derivative feedback controller, the actuating signal is the difference of proportional error signal and the derivative of the output signal. E A of t is equal to E of t minus kt into d c of t divided by dt. That means you can see the summation in that E of s is incoming and another one is c of s. That means E of s in the proportional side, proportional error signal and the derivative of the output signal. Okay, this two signals are coming for E A of S. Okay, E A of S is equal to E of S minus KT into S into C of S. The next you can see the simplified block diagram. The minor loop, it is a omega n square divided by S into S plus 2 zeta omega n and SKT. Those two blocks are in minor loop. You can see the minor loop, so it is negative feedback. If the negative feedback, then you should take as what we will write the transfer function for minor feedback loop. G, what omega n, that block is g of s, and feedback we will take as h of s. G of s divided by 1 plus g of s into h of s. This is for negative feedback. 1 plus g of s into h of s you will get for negative feedback. If it is positive feedback, then you will get 1 minus g of s into h of s. Okay, this is the block diagram simplified. We have simplified the minor loop. Okay, after simplifying, you will get omega n square divided by s square plus 2 zeta omega n plus kt omega n square whole bracket s. Okay, next is c of s divided by r of s. Again it is a loop. Okay, again it is a feedback loop. Then minor feedback loop. What we will write? G of s value is now omega n square divided by s square plus open bracket 2 zeta omega n plus kt omega n square close bracket into s. That is g of s. What is the value for h of s? There is no value, so we should consider as 1. Okay, now we will write for transfer function c of s divided by r of s is equal to g of s divided by 1 plus g of s into r of into h of s. Okay, h of s value is 1. If you solve that, omega n square divided by s square plus 2 zeta omega n plus kt omega n square into s divided by 1 plus omega n square divided by s square plus open bracket 2 zeta omega n plus kt into omega n square close bracket into s. If you solve that one, you will get omega n square divided by s square plus 2 zeta omega n plus kt into omega n square whole bracket s plus omega n square. Okay, after solving g of s divided by 1 plus g of s into h of s, you will get that equation. The characteristic equation is what will be the in the denominator, that is the characteristic equation. S square plus 2 zeta omega n plus kt omega n square into s plus omega n square is equal to 0. Therefore, the effective damping ratio, how we will find out the effective damping ratio? We will compare with the standard equation. The standard equation is s square plus 2 zeta dash omega n. We will take as 2 zeta omega n, but this is a addition of two values, so we are taking as 2 zeta dash omega n into s plus omega n square. That is the standard equation, so we will compare with the standard equation so that we will take as 2 zeta dash omega n is equal to 2 zeta omega n plus kt omega n square, so that zeta is equal to you'll get zeta omega n plus kt omega n divided by 2. The damping ratio increases, so the maximum overshoot is reduced. We know that E of s divided by R of s is open. E of s divided by R of s is 1 divided by 1 plus G of s into H of s. What is the value of G of s? Substitute. Okay, the value of G of s is omega n square divided by s square plus 2 zeta omega n plus kt into omega n square whole bracket yes. Okay, that you will get the value of G of s. That is the value of G of s. Substitute the value of G of s after LCM. After calculating, you will get the s square plus 2 zeta omega n s omega n plus kt omega n square into s divided by s square plus open bracket 2 zeta omega n plus kt into omega n square close bracket s plus omega n square. This is the equation you will get after solving. E of s divided by R of s is equal to, if you take out s common, then you will get s into s open bracket s plus 2 zeta omega n plus kt omega n square close bracket divided by s square plus open bracket 2 zeta omega n plus kt into omega n square close bracket s plus omega n square. For ramp input, R of t is equal to t, but R of s is equal to 1 divided by s square E of s. In that you substitute R instead of R of s. What you got in the above equation, E of s divided by R of s, instead of R of s, if you substitute the 1 by s square, you will get that equation E of s is equal to 1 by s square into s plus 2 zeta omega n plus kt omega n square divided by s square plus open bracket 2 zeta omega n plus kt into omega n square close bracket into s plus omega n square. Steady state error ESS is equal to limit s tends to 0 s into E of s. First cancel s square. Okay, if you cancel s square, then you go on substituting the s into 1 by s square. Again you will get s in the numerator, so s square in the numerator, s square in the denominator get cancelled. Later you substitute the instead of s 0, so that you will get 2 zeta omega n plus kt omega n square divided by omega n square. After solving, you will get 2 zeta divided by omega n plus kt. So with derivative feedback control, the steady state error increases. Next, we shall go for the proportional plus integral controller, that is PI controller. In this control, the actuating signal consists of proportional error signal added with integral error signal. In this, we have two signals added, that is proportional and integral. Okay, you can see that two blocks are in series. A of t is equal to E of t plus ki integration of E of t into dt. A of s is equal to E of s plus ki into E of s divided by s. If you integrate E of t, you will get E of s divided by s. Okay, that is the diagram for proportional plus integral controller, that is PI controller. You will get C of s divided by R of s. If the two blocks are in series, then we will add. Okay, after adding, then you will get a, if A block and B block, we will multiply. Sorry, if two blocks are in series, then we will multiply. Okay, if after multiplying, it is a feedback loop. Okay, it is a minor feedback loop. Then G of s divided by 1 plus G of s into H of s. That is what I have written here, s plus k I into omega n square divided by s square s cube plus 2 zeta omega n s square plus omega n square s plus ki omega n square. After solving, you will get this one. Okay, the characteristic equation is s cube plus 2 zeta omega n s square plus omega n n s square omega n square into s plus ki omega n square is equal to 0. That is the characteristic equation. E of s divided by r of s is equal to 1 divided by 1 plus g of s into h of s. G of s, what do you got? What is the g of s? S plus ki into omega n square divided by s square into s plus 2 zeta omega n. What is the value for h of s? If no value, then we will take as 1. E of s divided by r of s is equal to 1 divided by 1 plus g of s value. Next, E of s divided by r of s, you will get s square into s plus 2 zeta omega n divided by s to the power of 3 plus 2 zeta omega n s square plus omega n square divided into s plus ki into omega n square. E of s is equal to r of s into you substitute the r of s value, that is 1 by s square. After substituting, you will get the E of s is equal to, if s square get cancelled, then s plus 2 zeta omega n divided by s to the power of 3 plus 2 zeta omega n s square plus omega n square s plus ki omega n square. ESS is equal to limit s tends to 0 s into E of s. What you got the E of s equation, substitute in this. So s square get cancelled, you'll left with s. Okay, in the numerator s is there. If you substitute 0 into something, you will get 0. Okay, 0 divided by something also, you will get 0 only. So no need to solve, and you should write directly 0, because s into s plus 2 zeta omega n divided by s to the power of cube, that equation you'll get. So 0 into s, whatever you multiply, you'll get 0. So directly you write 0. For a system without integral controller, the steady state error for a ramp input is 2 zeta divided by omega n. Without integral controller, we got the ramp input is 2 zeta omega n. For a system with integral controller, the steady state error is the ramp input for is 0. The integral controller improves the steady state performance, but it may lead to oscillatory response. Next, we shall go for the proportional plus integral plus derivative controller. Now, three controllers we are adding: proportional and integral and derivative. Okay, the actuating signal consists of proportional error signal added with integral and derivative of error control. E a of t is equal to E of t plus kd into d e of t divided by dt plus ki integration of E of t into dt. E a of s is equal to, what we can write, E of s plus kd into s into E of s plus ki into E of s divided by s. E a of s is equal to, if you take out common E of s, then you will get 1 plus kd into s plus ki divided by s. Thank you.